recorded last time. So our first example, we're going to go ahead and go over the product rule. And it says whenever you multiply two bases that are the same, we're going to keep the base, write the base, and add the exponents. I'm going to show you guys why in a bit. Why is it true? Why do we have that? And then show you guys the easier way, or basically the rule. How do we do it without expanding every single work that we do, right? So here it goes. I'm going to go ahead and do the first one over here for x to the power of 3 times 2x to the power of 3. So yes, we do have our variable x in common. However, we have 4 and 2. 4 and 2 are what we consider the coefficients of our factors here. They're factors because we're multiplying the two items here. And because they're real numbers, it means that we can go ahead and multiply those together like regular numbers. So here we can go ahead and write 4 times 2. In this case, it would be 8. And over here, we have present how many x's? We have present our base, which is our x. And our rule says that we need to add their exponents. So we're going to add 3, and we're going to add 3. So we have our exponent of 3 on this factor, exponent of 3 on this factor. Therefore, we now have 8x to the power of 6, not to the power of 9, to the power of 6. Let me go ahead and expand it so you guys can see it. So what happened here? I have 4, right? Being multiplied by how many x's do I have here? I have 1, 2, 3. And then it's being multiplied by 2. And then 3 x's again. So if I put them all together, multiply 4 and 2, gives me 8. And I have 1, 2, 3, 4, 5, 6 x's. So if you need to expand it to double check your work, you can go ahead and do that. But the rule states that if you have the same base, all we have to do is just add the exponents. Okay? All right. So that's the first one. All right. What happens when we don't have that multiplication symbol in between our factors? What if we have parentheses instead? Well, if you have parentheses and you see that directly outside of my parentheses, there's no exponent. Let me go ahead and write no exponent present. Then we can go ahead and assume that these two factors are being multiplied together. So let's go ahead and write x to the power of 2, y to the power of, whenever it's not present, we're going to go ahead and automatically write a 1, because one y is present, multiplied by x to the power of 3 and y to the power of 4. I'm sorry if I said x instead of y before. I apologize. All right, so we're going to go ahead and treat it very similar to this. So we're going to keep the bases, add the exponents together. So I have a base of x and their exponents. It's 2 plus 3. And I have my second base, my variable y. And I'm going to add the exponents. So in this case, I have 2 plus 3, x to the power of 5. And 1 plus 4, we have y to the power of 5. So I'm able to simplify it here. Okay. So what's essential here? What's important? We need to know that whenever we have our real numbers, we're able to multiply them together. Don't treat them as variables. They're not variables. They're constants. They're real numbers. We can go ahead and multiply them together. Now, when we have variables, then that's when we keep our bases. We keep our base and we add the exponents. This is the product rule. Okay. All right. Ready for the next one? Okay. All right. Next one. We have our quotient rule, which means quotient means division. So this is the opposite of a product. Now, what happens when our terms here or our factors are being divided or divide each other, right? What happens? So whenever we have two bases and they're the same, we're going to go ahead and subtract the exponents. Keep the base, write the base, subtract the exponent. All right, so let me go ahead and now expand it so you guys can see it visually, what's going on. Here's my division bar. my fraction bar. My first term here, or my first factor, my first term, I have 5 x's. So I'm going to go ahead and write 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. And I have 6 y's. 1, 2, 3, 4, 5, and 6. All right. Below my division bar here, my fraction bar, my denominator, I have 1x and I have 2 y's, right? All right, so I expanded everything so you guys can see. Now, what happens here? Well, if I were to isolate these two first factors, x and x, it's stating that x is dividing x. All right, so what does that mean? Well, it means that whenever I have a number, for example, 1 divided by 1, our result is going to be 1. 2 divided by 2, our result is going to be 1. 3 divided by 3, the result is going to be 1. No matter what number I have on my numerator, if it's the same on my denominator, it's going to always be equal to 1. And you can go ahead and write your cat divided by your cat. In that case, your result will always be 1. So no matter what we have on your numerator, if it's the exact same item or the exact same factor that you have on your denominator, then it's going to simplify to 1. So what happens to these two? They simplify to 1. They don't get canceled, they just simplify. Very similarly, we can go ahead and do that to our next pair of factors here, y over y, and these two as well, y over y. All right, so how many are we left with? We're left with 1, 2, 3, 4. 4 x's on my numerator, so x to the power of 4. And we're left with 1, 2, 3, 4. 4 y's. So y to the power of 4. And that's our result. Now, how do I use the rule here? I expanded so you guys can visualize why it happens. Now I'm going to apply the power rule. So in this case, I have x, I keep the base, and I have 5 minus 1 times, keep the base, y to the power of 6 minus 2. I simplify x, 5 minus 1 is 4. And 6 minus 2 is also 4. So it gives us the same result. What's happening? We're doing that rule where it's eliminating. Any questions on this one? You're going to see sometimes that your exponent is greater on the bottom. We apply the same rule, except we keep the greatest exponent or the term wherever the greatest exponent is. For example, we have x to the power of 5, x to the power of 1. 5 is greater than 1, therefore everything is kept on our numerator. I'll go over the next example so you guys can see the negative when we have negative exponents. Okay, all right. Any questions on this one? If you need to, I can come back to this one. All right, let's continue. Number 3, zero exponent rule. It means that any base raised to the power of 0 is equal to 1. So what is that telling us? It's telling us that whatever we have, no matter what the base is, if its exponent is 0, the whole entire term is going to be equal to 1. It can be y to the power of 0. It can be 2 to the power of 0. It can be, I don't know, x, y, and z. All of it raised to the power of 0. No matter what it is, if it's raised to the power of 0, then it'll be automatically 1. Why is that true? All right, so let's go ahead and say that x is to the power of 1. This is saying that we have 1 times x, right? We multiply the factor 1 time. Okay, what happens if we have x squared? We have 1 times x times x. If we have x to the power of 3, 1 times x times x times x. And it continues on, right? X to the power of n n times, many times, 1 times all the way to n times, right? So however many times however big our exponent is. Now, if we have x to the power of 0, in this case, we have 1, but we're not multiplying the base any more times. So notice that it's not times 0, it's just no multiplication of the term any times. So it's not being multiplied any time. So we just keep our term of 1 times basically nothing. So that's why it's possible, or why it's true, that we have x to the power of 0 equals 1. So it's not just because it's to the power of 0, it's just because we're not multiplying the term any more times. All right. Let me go ahead and clear. That was the 0 exponent rule. Now here comes my favorite one, the power rule. So this one says to raise the power to another power. So basically we are Super Mario and we're like now Super Ultra Mario. So we like raise our power one more time. We multiply, we keep the base, and we multiply the exponents. So what's happening here? Well, we have this term that's inside of our parentheses, y to the power of 4. And notice that this time, our exponent is directly outside of our parentheses. Very different to the power rule. The power rule, they're multiplying each other. This one has an exponent directly outside our parentheses, no base. Basically, the base is everything inside of our parentheses, okay? All right, so how do we do this one? This one's telling us that whatever's inside, we're going to multiply it however many times our exponent is being present outside. So in this case, y to the power of 4 is being multiplied 3 times. So we have y to the power of 4 multiplied by 1, multiplied twice, and multiplied 3 times. So 1, 2, 3 present here. So it's y to the power of 4, which is our base here, being multiplied 3 times. Therefore, we can go ahead and now use our product rule. The terms are being multiplied together. We keep the base, and we add the exponents. So 4 plus 4 is 8, plus 4 is 12. Very similarly, we can go ahead and multiply 4 and 3 in this case, which is y to the power of 12. So that's what's happening. It's being multiplied 1, 2, 3 times, because that's how many times our exponent is telling us, and then whatever is inside. I'm going to go ahead and expand a little bit more, especially when we have fractions and more terms inside. Let's see what happens there. I'm sorry if I'm going too fast. Let me know if you need me to go back to any of them. Also, look through your examples. Let me know if you want me to go through any of the examples as well. We have 2 more rules. I'm going to go ahead and expand the power rule, and I'm going to also explain the negative exponents as well. All right, let me go ahead and clear and go on to our next one, our expanded power rule. So here it's telling us whenever we have multiple factors inside of our parentheses and we have a power outside, it's telling us that we can go ahead and distribute that power to every single factor that's inside, every single factor on the numerator and denominator. So with that said, whenever we have an example like this, notice here that it's already simplified inside. We can go ahead and either simplify inside and then distribute, or we can go ahead and distribute, then simplify. It's totally up to us on which procedure we want to follow. I like to simplify inside and then distribute so I don't deal with huge or big quantities of numbers. So for example, 4 to the power of 3 or 16 to the power of 3, that's going to be a large number like 4,096. And then having to simplify, I'd rather simplify first and and then distribute that power that's outside. Okay, What do I mean? I mean that I'm going to simplify what I have in here first. So I have 4x to the power of 5, y to the power of 1, 16 to the power of times x to the power of 1, and y to the power of 4, all multiplied by 3. What I'm going to do, I'm going to go ahead and focus my real numbers with my real numbers with the coefficients. So I have 4 divided by 16. It's a fraction. So here we can go ahead and reduce it not to 4. It's 4 divided by 16, not 16 divided by 4. It's going to be 1 over 4. So I'm going to leave my 1. Do I need to write it out? No, I do not. Write my fraction bar. I'm going to write my 4 underneath. And now I have my next term. I have x to the power of 5 and x to the power of 1. I know I have to subtract these two. I know I get left over 4. 5 is a bigger exponent, so I leave x to the power of 4 above. Now here, these two, I have y to the power of 1, y to the power of 4. I subtract these two, I get 3. However, y to the power of 4 is greater, so I leave y to the power of 3 on my denominator. So this is what I was trying to explain when I was doing the quotient rule. So whichever exponent is the greater number, that's where we're going to keep our term to keep it positive, and I'll go into negative numbers right now. Okay, so here in this case, yes, we do subtract it. If I were to keep it on the numerator, it'll be a negative exponent, but I want to keep it positive, so I keep it below. All of this to the power of 3. Now we can go ahead and distribute our beautiful exponent to every single term that's inside, every single factor. So multiply 3 times 4. 4 has an exponent of 1, so we're going to multiply to that exponent, and y has a power of 3, so we're going to go ahead and multiply to that exponent. All right, here we go. We have x to the power of 4 times 3, 12. 4 to the power of 1, 1 times 3 is 3. And y to the power of 3, 3 times 3 is 9. Okay, one last step. Since we do have a real number and we can go ahead and simplify that. We have x to the power of 12. 4 times 4 times 4. Well, 16 times 4, which is 64, times y to the power of 9. So this one was a little bit complicated. It was a little bit longer, had more steps. And yes, it involved including the quotient rule. But what's happening here is that the exponent that's directly outside is being distributed to both the numerator and the denominator. And we multiply to each of the exponents that are inside. So I simplified first. Then distribute. The power. And then continue to simplify. Any questions on this one? I know this one was a long one. Okay, now I'm going to address the negative exponents. Let me go ahead and save an image. Let me clear. Let me go on to the last one. Number 6, negative exponents. So it says right here, if you factor a numerator or a denominator and it's moved across the fraction bar, the exponents can be changed. So the signs of the exponents can change. So for example, if whenever you're subtracting, let's say for our last example we had, what was it? I think it was, let me go back. Y to the power of 1 and y to the power of 4. So in this case, if you were to apply the quotient rule, you would end up with y 1 minus 4, y to the power of negative 3. In order for us to make this power happy, because it's negative, we can change it from the numerator to the denominator. Basically, what it's saying that we have the inverse of it. So in order for us to make it positive now, we would write 1 and y to the power of positive 3 now. So we have basically the inverse. So in order for us to make it happy, we can change it from the numerator to the denominator. So how we or why we are being allowed to do this, it's because it's what we call the inverse of it, right? So very similar to this, in order for us to solve this one, yes, we can go ahead and apply the product rule, the quotient rule, sorry, and then see if we get a positive value from then, or we can go ahead and automatically make this exponent happy by switching it to the top, or our numerator, and make this exponent happy by switching the term to the bottom. And then applying the quotient rule, obviously, because they have the same base. And continue to simplify. So here we have x to the power 7. We can apply the quotient rule here directly if we wanted to. It would be -1 minus -8. Keep, change, change. We have -1 plus 8, x to the power of positive 7. Either way, it would give us the correct answer. Whichever method you want to use, again, these are the rules that happen. So very similar to the power rule. If it's a negative outside, we then distribute everything to the inside, or we can go ahead and flip. So one of the examples that you're going to see on your homework are, for example, let's see, 2x to the power of 2, y z to the power of 3, all over, let's say, 4x, y to the power of 2, and z to the power of 10 to the power of -2. So in order for us to switch this to a positive 2, to a positive squared value, we can switch the whole entire fraction, which is 4x, y to the power of 2, z to the power of 10, over 2x squared, y, z to the power of 3, all being to the power of 2. So from here, we can go ahead and make it positive by just switching the whole entire fraction, okay? I hope I covered mostly everything here. But look through your questions. Let me know if you need me to go through any of them. I'm more than happy to do so as well. And I'll go through them as